Hello everyone, my name is NARAYAN and I am thrilled to present today on a topic that sits at the intersection of physics and information science, information theory and entropy in physical systems. Entropy is the unifying concept across many domains from communication system to thermodynamics. The presentation will guide you through the foundations of the real-world applications in fields like quantum computing, machine learning and data compressions. We will start the basics of information theory and build towards its broader implications in physical systems. To begin, let's understand what informed theory is. At its core, it's a mathematical framework developed to study the transmission and processing and the storage of information. Claude Shannon, the father of information theory, formalized in his landmark 1948 paper. He introduced revolutionary ideas like entropy in the context of information and channel capacity. This concept showed how to quantify the information and channel capacity. This concept showed how to quantify information and how to transmit it efficiently and reliably over the noise communications channels. And this field touches a wide range of disciplines: mathematics, computer science, electrical engineering, and statistics, because it's so fundamental to how data and signals behave. Entropy, which we will explore more deeply in the coming slides, is central to this theory because it tells us a system how much information or uncertainty is involved in a system. Entropy can sound abstract, so here's an initiative way to think about it. Entropy is the amount of uncertainty or surprise associated with a random variable and process. Let's take a flip a coin. If the coin is fair, there is an actual chance of head or tails. We we cannot predict the outcomes with certainty, so entropy is relatively high. Now compare the possible outcomes a process has. The more evenly those outcomes are distributed, the higher its entropy. From the information perspective, energy is the average surprise or the average number of bits needed to encode the outcomes. This links to the idea of disorder in the physical systems, which we will return to when we discuss the thermodynamics. Next thing, let's go a bit more technical with the Shannon's definitions of entropy. Entropy is given by the formula Hx minus summation of Pxi and log 2 Pxi. This equation calculates the average information content of a random variable x. Let's say x represents the character in English sentence, and this most frequently a letter appears. The less information it carries when we see it, the rare letters like Z are more informative than common ones like E. Each term in the sum represents the probability of an outcome modified by the information it carries. Summing over all the outcomes gives the expected average informations per event. Shannon entropy is measured and in bits when the logarithm is base 2. Entropy is at its maximum when the distribution is uniform, when every possible outcome is equally likely. That's when we know the least and therefore have the most uncertainty. Now let's move from the information to the physics. In thermodynamics, entropy was first formalized by Ludwig Boltzmann. He defined it as the delta S is equals to kb Boltzmann constant dot ln W, where S is entropy, kb is Boltzmann constant, where W is the represents the number of microstates or microscopic configurations of a system. Thermodynamics entropy measures the physical disorder. For example, a gas in a container has higher entropy when it's spread out rather than compressed. This aligns with the second law of thermodynamics, which states that in an isolated system, entropy tends to increase over time. That means systems naturally evolve toward greater disorder. What's fascinating is that thermodynamics shares similar structure with Shannon's entropy, connecting the uncertainty in masses with the disorder in molecules. Next thing we are going to discuss about here's where the worlds of information theory and physics really connect. Claude Shannon chose the word entropy deliberately because its mathematical expression resembled Boltzmann's. In both cases, entropy measures uncertainty. In Shannon's case, it's uncertainty in the mass's content. In the Boltzmann case, it's uncertainty in molecular configuration. When all outcomes are equally likely, Shannon's entropy simplifies to the log base 2 W, similar to the Boltzmann's ln W. This deep equivalence shows that the both type of entropy about the counting possibilities, whether they are bits or molecules. This sets the structure with what allows us to bridge concept between the information theory and thermodynamics. Let's take a moment to recognize the two pioneers behind these ideas. Claude Shannon was a mathematical and electrical engineer, and his 1948 paper laid the foundation of all the modern digital communications. He introduced the concept like the bit entropy and the channel capacity, all of which we still use today. On the other hand, the Ludwig Boltzmann was 19th century physicist who developed the statistical mechanics. He connected the microscopic behavior of atoms to microscopic thermodynamics quantities like temperature and entropy. Both thinkers working in different centuries fields introduced entropy as a way to quantify uncertainty, one in data, other in physical matter. Their works remain foundational in both modern physics and information science. In other words, entropy has more practical applications in computer science. First, in data compression, energy tells us the minimum number of bits required to encode data without losing information. Algorithms like Huffman coding rely directly on entropy calculations. In cryptography, high entropy keys are harder to guess, making them more secure. Energy is crucial for randomness in encryption. If we think about machine learning, entropy is used in decision trees to split the nodes based on the information gain, and in the loss functions like cross entropy during model training. Finally, a Kolmogorov complexity, a related concept, measures how compressible a data set is, linking algorithmic information to entropy. These examples show how entropy guides us in designing more efficient, secure, and intelligent systems. Entropy also plays in this slide. We are going to explain like entropy in communication, coding, and compression. Entropy can also plays a central role in communication system, particularly in coding and compression. There are two main types of coding: source coding and channel coding. Source coding is all about compression. Algorithms like Huffman coding and arithmetic coding are designed to minimize the number of bits needed to represent data. The closer compression algorithm gets the entropy of the data, the source, and the more efficient it is. This is essentially the Shannon's limit, the theoretical minimum length of encoded data. Channel coding deals with the errors during transmission, and the noise in channel can flip bits as you introduce the redundancy to detect and correct these errors. Let us, for example, CRC, cyclic redundancy check. It is used in the networking, and Reed-Solomon codes are used in the CD and DVDs. These codes clearly balance the entropy and reliability, adding just enough redundancy to preserve data integrity without wasting too much space. Together, source and channel coding ensure that the information is transmitted both efficiently and accurately, even over noisy or loosey channels. If we think about real-world applications regarding to the compression algorithms, this slide gives concrete examples of how entropy-based principles are applied in compression algorithms used daily. Let us say zip. It has lossless compressions. Zip combines directory-based methods like LZ77 or LZ78 with entropy coders like Huffman coding. This allows it to approach the theoretical minimum file size which is governed by Shannon's entropy. Another one is JPEG format, lossy image compression. JPEG first reduces the redundancy using the discrete cosine transform and quantization. Then it applies entropy coding to compress the quantized value efficiently, taking advantage of the fact that certain pixel patterns are more common than others. If we think about MP3 for audio video compressions, these codes, these codecs use the Fourier transforms (FFT) or similar methods to break down the signals followed by quantization and entropy coding. They remove data that's perceptually irrelevant and then compress what remains using the entropy models. The key idea here is that the entropy helps identify and remove the redundancy. These algorithms don't just store data, they exploit probability distributions to represent it more compactly. In this slide, let's step back and look at the bigger picture. Information theory and entropy are not just theoretical ideas. They shape modern technology, our understanding of the physical world. Whether we are compressing files, analyzing biological systems, or building quantum computers, or the principles of entropy always apply. Entropy tells us the limit of what we can know and do in any system, from the most basic binary signal to the most complex molecular interaction. In network optimization, it helps us model data traffic and detect anomalies. In quantum mechanics, it helps us to ensure the entanglement and the information flow. Even in biology and evolution, the entropy is used to analyze the genetic information and the biological order. So, understanding entropy helps us in both understanding nature and designing the efficient system for communication, computing, and beyond. Next thing, we are going to discuss about compression algorithms exploiting redundancy via entropy. These slides take a deeper look at how compression algorithms use entropy to remove redundancy. Zip compression is dictionary-based methods like LZ77 or LZ78, which build a system of table of repeated sequence. Then it applies the entropy coders like Huffman or arithmetic coding to encode references efficiently. JPEG image compressions use the DCT. It's called discrete cosine transform to convert spatial data into frequency components. The higher frequency components, which often carry less visual information, are quantized more aggressively. Then entropy coding compresses the result. Audio video MP3 that follows a similar logic. They transform the signal into frequency space and quantize the components, and then encode them using the entropy aware coding. The key is this: the entropy tells us which part of data occur most often and can be encoded with fewer bits. These algorithms are intelligent. They compress without removing the important information, guiding by statistical probabilities. Shannon's capacity formula is fundamental result in the information theory. We can calculate using this formula, where C is the channel capacity bits per second, and B is the bandwidth, S by N is the signal to noise ratio. This formula tells us the theoretical maximum rate at which the information can be transmitted over the noisy channel without the error. To achieve this rate, we need efficient encoding and robust error corrections. LDPC is one of them, and turbo codes are advanced error correction codes that come very close to the Shannon limit. There is the iterative decoding and probabilistic models based on the entropy to maintain the accuracy with minimum overhead. In addition, entropy in network analyzes helps us detect traffic anomalies. For example, sudden drops or spikes in entropy across network packets may signal a denial of service attack or extrafiltration. So the entropy isn't just theoretical; it is used to make the networks faster, safer, and more efficient. Now let's visualize entropy with the two powerful examples. Thermodynamic entropy. Imagine a container with a glass molecule separated by a partitions. When the partition is removed, the molecules spread out, fill the space. And this represents the increase in entropy, and the system becomes more disordered. This visualization illustrates the second law of thermodynamic system tends to evolve toward the higher entropy or greater disorder. Second example is related to the information entropy. Consider two binary strings. First one, all zeros, has very low entropy. It's predictable. But second one, it's consists of zeros and ones in a bits, and it has the higher entropy. It's random. Its randomness, hard to compress. This shows how entropy quantities uncertainty in both physics and data systems. The same concept measuring disorder applies whether we are talking about molecules or binary data. Entropy remains at the edge of the research across multiple domains. Let us say quantum entropy. The concept of entropy of entanglement measures the quantum correlations between particles. This is essential in quantum computing and quantum communications, where understanding correlations between the particles. This is essential in quantum computing and quantum correlations, where understanding entanglement is key to the building reliable systems. Second one is machine learning, where entropy is used in a cross entropy loss functions for classification problems. This information bottleneck theory applies entropy to compress model representations while preserving relevant informations. Second one is thermodynamic of computing, where the Landwehr's principle connects information erasure with the heat generations and informing research on reversible and thermodynamically efficient computing. Fourth option is data security, one of the applications, where entropy is used to access the randomness in encryption keys. It also helps to detect our anomalies in big data by identifying unexpected patterns or outliers in the entropy matrix. This advances so that the entropy is not a finished chapter, it's a living, evolving concept that continues to guide innovation. To wrap up, let's recall the key takeaways. Unified concept. Whether we are looking at data or molecules, entropy measures uncertainty. Shannon's and Boltzmann's formula have the same mathematical form because they both count possibilities, just in different domains. Let us discuss what foundational theories. Cloud Shannon, Cloud Shannon laid the groundwork for digital communications, and Ludwig Boltzmann provided the statistical foundation for thermodynamics. Their work created a bridge between the abstract information and the physical systems. Their crucial practical roles. Here, entropy guides data compressions, encryption, error correction, and machine learning. It defines the limits of what's possible in computing and communications. Third part is about their relevance. From quantum computing to artificial intelligence, entropy remains essential. It not only explains how systems behave, but also helps us to build better ones. So understanding entropy is not just about theory, it's about harnessing disorder and uncertainty to solve the real problems. Here are the references I use to support these presentations. They include the foundation source like Wikipedia entries on entropy and Shannon's theory, as well as scientific articles on recent developments like quantum theory, quantum entropy. If you are interested in diving deeper into these topics, I highly recommend these resources. Thank you for your attention. I will be happy to take any questions that you can comment on comment section. Thank you.